Good morning. Today we shall start with the third chapter of quantum mechanics, theory of angular momentum. This chapter deals with the systematic treatment of theory of angular momentum and related topics. The reference textbook is the same as the one we used for the first two chapters, Modern Quantum Mechanics by J.J. Sakurai and Jim Napolitano. The first section in this chapter is rotations and angular momentum commutation relations, and the first topic we shall discuss is finite versus infinitesimal rotations. Now, why do we start by discussing rotations? The reason is that we are going to use the same strategy that we used in the first chapter. If you remember, in the first chapter, we defined linear momentum as the generator of space translations. And from the property of space translations that we already know, we were able to obtain the commutation relations satisfied by the components of linear momentum. Here we shall use the same strategy. We are going to define angular momentum as the generator of rotations. We know something about the properties of rotations, and from those properties we are going to obtain the commutation relations satisfied by the components of angular momentum operator. And one of the important things that we already know about rotations is that rotations about different axes, finite rotations about different axes, do not commute. We have already seen this, for example, when we discussed rigid body motion. Now, for example, if you are trying to make a rotation, right? Suppose you are making a rotation about the z-axis by an angle pi by 2, and then follow it by a rotation about x-axis by an angle pi by 2. Okay, so here the notation is as follows. Rz means the rotation is about the z-axis, and the argument is the angle of rotation. So you are taking an object, rotating it about the z-axis by pi by 2, and then following the first rotation by a second rotation, but now about the x-axis, again by the same angle pi by 2. We know that this is not the same as Rx of pi by 2. This is not equal to Rx of pi by 2. Sorry, this is not equal to Rz of pi by 2, Rx of pi by 2. Okay. Here we are making the first rotation about the x-axis and then following it by a rotation about the z-axis. Now, this is the reason why we say that finite rotations do not commute. We can easily see this in this picture here. What we wrote down over there was Rx of pi by 2, Rz of pi by 2 is not equal to Rz of pi by 2, Rx of pi by 2. Right? You are supposed to read this from the right. This is the first rotation followed by the second rotation. Let's look at an object of this shape. Okay. Now first you make a rotation about the z-axis. This is the z-axis here. And the convention we are using is that the positive sense of rotation is the rotation in the counterclockwise direction. Right? So the first rotation here is about the z-axis by an angle pi by 2 in the counterclockwise direction about the z-axis. So you have to look from the top and rotate this in the counterclockwise direction. Once you make this rotation, the orientation becomes as the orientation is as given in this picture. All right? I think this is obvious. You just rotate it counterclockwise about the z-axis. Now you follow it by a rotation about the x-axis by an angle pi by 2. Okay, so this is the x-axis. You just make a rotation in this direction. All right, a counterclockwise direction about x-axis by the same angle pi by 2, and the final orientation is given here. Okay, so this is the result of Rx of pi by 2 multiplying Rz of pi by 2. Okay, again, as I said, you read it from here. First Rz of pi by 2 followed by Rx of pi by 2. Now let's do it in the opposite order. First, let's make the rotation about x-axis by the same angle pi by 2. Right? So you start with the same orientation as we had here. You first make a rotation about x-axis by pi by 2. Okay, you just rotate it like that and you get this orientation. All right. Now you make a rotation about z-axis again by an angle pi by 2, as we said, in the counterclockwise direction. Okay, you see that the final orientation is as given in this picture. Clearly we see that these two are not the same. The final orientation is different depending on which rotation was carried out first. Okay. So this clearly illustrates that finite rotations about different axes do not commute in general. This is something that we have already seen in classical mechanics also. We have just seen qualitatively that rotations about different axes do not commute. But we need to work out quantitatively the manner in which rotations about different axes fail to commute. For this, let's just look back at rotations in 3 dimensions. We know that rotations in 3 dimensions can be represented by 3 by 3 real orthogonal matrices. Okay. For example, if you consider a vector v vector which has components vx, vy and vz, when you make a rotation, these components turn to a different set of numbers vx prime, vy prime and vz prime. These are the old components and these are the components after rotation. And these components here, Vx prime, Vy prime, Vz prime, and the components Vx, Vy, Vz, the old components and the new components are related via a rotation matrix. Okay, this is a 3 by 3 orthogonal matrix. We have already learned that this is a 3 by 3 orthogonal matrix. Okay. Uh, an orthogonal matrix is a matrix whose transverse is the same as its inverse. In other words, R is an orthogonal matrix if R transpose is equal to R transpose R is equal to the identity matrix. Okay. Now, if these matrices are orthogonal, it's easy to show that the length of the vector remains unchanged under a rotation. That is, square root of Vx square plus Vy square plus Vz square is equal to square root of Vx prime square plus Vy prime square plus Vz prime square. Okay, so the orthogonality of the rotation matrix actually ensures that the magnitude of the vector remains the same under a rotation. In general, the lengths do not change under rotations. Okay. To be definite, let's consider a rotation about the z-axis by an angle phi. Before we go into that, let's have a word on the convention that we follow. In the convention that we follow, a rotation operation affects the physical system itself. So when we talk about a rotation, we are talking about rotating the physical system. The coordinate system itself remains unchanged. In literature, this viewpoint is often referred to as the active viewpoint of rotations. Active viewpoint. So in the active viewpoint, if you have a vector v vector, under an active rotation, we rotate this vector by an angle phi. We rotate this vector by an angle phi. Okay, now we have a new vector, v vector prime. The coordinate axes themselves remain unchanged. This is the active viewpoint. In the passive viewpoint, the coordinate axes are rotated, right? So we have a vector here. Let's call this as v vector. In the passive viewpoint, the coordinate system is rotated. So initially we have a coordinate system denoted as xy, coordinate system with axis xy, and we rotate the coordinate system by an angle, let's say phi. Okay. And this is the new coordinate system. This would be x prime, y prime. This is the passive viewpoint. So we shall be following the active viewpoint. Now also, the angle phi is taken to be positive when the rotation is in the counterclockwise direction. So if we are talking about a rotation about the z-axis, then the positive angle corresponds to a rotation in the counterclockwise direction, which is denoted here, right? So this is a rotation in the counterclockwise direction. Let's say about the z-axis. This is the positive z-axis, and this is the xy plane. So the rotation is in the xy plane, and when viewed from the side of the positive z-axis, the angle of rotation, the rotation is in the counterclockwise direction. In this case, we say that phi is positive. Alright, so this is the convention we shall be following. Now with this convention, the rotation matrix corresponding to a rotation of the vector or rotation of the physical system about the z-axis is given by Rz of phi is equal to cos phi minus sin phi 0, sin phi cos phi 0, 0, 0, 1. Okay. It's easy to derive this rotation matrix. We could look at this example, right? So let's consider a vector. Let's consider the following rotation, right? So we are in the xy plane. We are in the xy plane. This is the z-axis coming out of the screen. This is the positive z-axis. We have v vector here, and let's say that this v vector has been rotated to v vector prime. Okay, this angle is phi. The angle of rotation is phi. Okay, we could denote this angle as theta, and then this entire angle, the angle between v vector prime and the x-axis, is phi plus theta. It's clear from here. This angle is phi, this angle is theta, and this entire angle, the angle that v vector prime makes with x-axis, is phi plus theta. Okay, this is actually sufficient to determine this rotation matrix. Let's look at the components of v vector prime. The first component is denoted as vx prime. We know that this is equal to modulus of v vector prime cos of the angle between v vector prime and x-axis, which is phi plus theta. This is cos phi plus theta. Okay, but we know that we are considering a transformation, a rotation, such that the magnitude of the vector does not change. So we have the condition modulus of v vector prime is the same as modulus of v vector. Okay, so we can write this as v cos phi plus theta, where v is the modulus of v vector. So we denote both this as v. Okay. Now we can use the trigonometric identity. V cos phi plus theta is v cos phi cos theta minus v sin phi sin theta. Okay. But now if you look at this v cos theta, right, the v cos theta appearing here, the v cos theta appearing here is actually the x component of vector v. Right. So this angle is theta. As you can see, this angle is theta. So v cos theta is actually the x component of vector v. So we can write this as vx. V cos theta is vx. So this becomes vx cos phi minus, similarly, v sin theta is the y component of vector v. And this is v sin phi. Sorry. V sin theta is vy. So we have vy sin phi. Okay. Similarly, vy prime, the y component of vector v vector prime, right? The y component of v vector prime is given by modulus of v vector prime, which is the same as v, and sine theta plus phi. Okay. Now we can again use the trigonometric identity for sine a plus b, and this becomes v sine theta cos phi plus v cos theta sin phi. Okay, because sine theta plus phi is sine theta cos phi plus cos theta sin phi. Again, v sine theta here is vy. So this is vy cos phi plus v cos theta is vx sin phi. Okay, vx sin phi. And vz prime itself remains unchanged. It's the same as vz. Alright, because we are rotating the vector in the xy plane. So the z component does not change. There's no change in the z component. Alright. So this is what we see in this matrix here. Right? So we have vx prime is equal to vx cos phi minus vy sin phi. Alright, plus we could write 0 multiplied by vz. Right? There's no contribution from vz here. Here it's vy cos phi plus vx sin phi plus 0 multiplied by vz. Okay, and vz prime is vz itself. Right? So we can write this as 0 multiplied by vx plus 0 multiplied by vy plus 1 multiplied by vz. This is vz prime. Now we can write this as a square matrix. Okay, so let me write it here. You can write this as a square matrix like this. On the left side, we can write the column matrix involving vx prime, vy prime, and vz prime. Okay, and on the right side, we have the column matrix involving vx, vy, and vz. But we already have found out the relation between vx prime, vy prime, vz prime, etc. on the one side, and vx, vy, vz on the other side. Right? So here we have Vx prime is equal to Vx cos phi. So when we multiply this, we have a square matrix here. Vx prime has to be Vx cos phi, okay, Vx cos phi minus Vy sin phi. All right, so we put a minus sin phi here, and there's no contribution from Vz, so we write it as 0. Okay, 0. That this line gives this equation. Right, the first line in this matrix multiplication gives us this equation: Vx prime is equal to Vx cos phi minus Vy sin phi multiplied by plus 0 multiplied by Vz. Okay. Similarly, the second line gives us Vy prime, and Vy prime is Vy cos phi plus Vx sin phi. The Vx here has to be combined with the sin phi here, right? And there's a cos phi. Again, there's no contribution from Vz, so it's again a 0 here. And Vz prime is the same as Vz, no contribution from Vx or Vy, so this is simply 0, 0, 1. Okay, that's the matrix that we have here. Rz of phi is equal to cos phi minus sin phi 0, sin phi cos phi 0, 0, 0, 1. This gives us the rotation matrix corresponding to a rotation about the z-axis by an angle phi and in the active sense. Okay, so this is the rotation matrix. In the same way, you could find the rotation matrix for rotation about x-axis and rotation about y-axis. Right? In the first case, for rotation about z-axis, we took the axis like this: x, y, and z. Right? So this is the axis about which we are making the rotation. Now, if you want a rotation about x-axis, right, you just take a cyclic permutation so that it remains a right-handed coordinate system. So we change x to y, right? We change x to y, y to z, and z to x. All right. So instead of x here, we denote this as the y-axis. Instead of y here, we'll denote this as the z-axis, and instead of z here, we denote it as the x-axis. Now you could do exactly the same thing, and you would get the rotation matrix corresponding to an angle phi about the x-axis. Okay, the only thing to get Rx of phi from Rz of phi, right, you can look at these equations and just make this change. You just change x to y, y to z, and z to x, right? And in order to get the rotation matrix about y-axis, right, corresponding to an angle phi about the y-axis, we again take a cyclic permutation. You take y, change y to z, z to x, and x to y. Okay, this would, and it could do exactly the same thing, and that will give us the rotation matrix by an angle phi about the y-axis. All right, so in this way we can find Rz of phi, Rx of phi, and Ry of phi. Okay. Now, if we had used a different convention, the passive viewpoint, for example, all right, in the passive viewpoint, a physical system remained fixed, but the coordinate axes are rotated. The same matrix, right? We would get the same matrix with a positive phi, but it would represent a clockwise rotation of the x and y axis. Right? You could try that. So the same matrix in the passive viewpoint, the same matrix. This is in the active viewpoint for a counterclockwise rotation of the vector itself, right? But the same matrix corresponds to the rotation matrix in the passive viewpoint for a rotation of the coordinate axis, right? In the passive viewpoint, this is the rotation matrix of the coordinate axis by an angle phi in the clockwise direction. Okay, the clockwise direction. All right. So it's clear that a rotation of the vector itself in the counterclockwise direction by an angle phi is mathematically equivalent to a rotation of the coordinate system by an angle phi in the clockwise direction. All right. The transformation equations, the way in which the new coordinates, sorry, the way in which the new components and the old components are related remains the same for a passive viewpoint in the clockwise direction and an active rotation in the counterclockwise direction. Okay. but we have already seen these things before. This is just a revision. Now what we are interested in is an infinitesimal form for Rz. Right? We have the rotation matrix here. We have the rotation matrix here about z axis by an angle phi. This is the rotation matrix that we have just derived. We need an infinitesimal version of this. It means that we are looking for a version of this matrix when phi is very small. Okay. So for this we can use the expansion for cos x and sin x. So cos x, you can look it up, and cos x can be expanded as 1 minus x squared divided by 2 factorial plus x raised to 4 divided by 4 factorial minus etc. Okay, and sin x can be expanded as x minus x cubed by 3 factorial plus x raised to 5 divided by 5 factorial. So we are looking at Rz of epsilon. Right? So instead of phi, we have epsilon, where epsilon is a very small quantity. It's a very small angle. It's an infinitesimal angle. So what we do is that we write epsilon instead of phi here, and then use this expansion, retain only up to the second order terms in epsilon. Right? So we'll retain only terms up to epsilon square. So cos phi here would become, for example, cos epsilon, which can be written as 1 minus epsilon square divided by 2 factorial, and the other terms are higher order terms, so we neglect them. Right? So that's a term here in Rz of epsilon. Okay, and look at this term minus sine phi. So if you put epsilon instead of phi here, sine epsilon would become epsilon minus epsilon cube divided by 3 factorial plus etc. But this is already third order, and we said we would retain only up to the second order terms. So sine epsilon we have to write as epsilon itself, and minus sine epsilon is minus epsilon. Similarly, sine phi becomes epsilon here, and cos phi here also becomes 1 minus epsilon square divided by 2. So this would be the matrix corresponding to an infinitesimal rotation about the z-axis up to the second order. Okay, the terms of order epsilon cube and higher order are ignored. Okay. Similarly, we can find the rotation matrix for Rx of phi, as I explained before, and then again take the infinitesimal version of this and write it as Rx of epsilon. We just have to use the same expansions. And Rx of epsilon, I ask you to try this. So find Rx of phi plus and then take the infinitesimal version. Retain only terms up to the order of epsilon square. Okay, and Rx of epsilon becomes the matrix 1 0 0 0 1 minus epsilon square divided by 2 minus epsilon 0 epsilon 1 minus epsilon square divided by 2. Similarly, let's also find Ry of epsilon, which gives the square matrix with the elements 1 minus epsilon square divided by 2, 0 epsilon 0 1 0 minus epsilon 0 1 minus epsilon square divided by 2. Okay, so now we have infinitesimal rotation matrices for rotation about the z-axis, rotation about x-axis, and for rotation about y-axis. Okay. Now we want to calculate quantitatively how exactly these rotations do not commute, all right? How exactly do they fail to commute? So let's first find Rx of epsilon multiplied by Ry of epsilon. What does this mean? This is an infinitesimal rotation about the y-axis followed by an infinitesimal rotation about x-axis. Okay, both rotations are by an infinitesimal angle epsilon. Right? So we just have to multiply the matrices. We have Rx of epsilon here and Ry of epsilon here. You know how to multiply a matrix, right? So you can multiply these two matrices to get another square matrix. Just remember that when you multiply, whenever you get a term of order higher than epsilon cube, right? A term with a higher order term. Whenever you get a higher order term like epsilon cube, etc., they can be neglected, right? After multiplying, retain only terms up to the order of epsilon square, and that gives you this matrix. Okay, leave it as an exercise for you to do this matrix multiplication. So the product of the matrices Rx of epsilon, Ry of epsilon gives us this square matrix. Alright, so this would be the square matrix corresponding to two rotations, one first about the y-axis by an angle epsilon, and then about the x-axis by an angle epsilon. Okay, we can also find the rotation. We can also find the product of the rotation matrices corresponding to rotations in the opposite order. What we found just before was Rx of epsilon multiplying Ry of epsilon. This is a rotation about y-axis followed by a rotation about x-axis. Now let's find the same thing for a rotation about x-axis followed by a rotation about y-axis. First a rotation about x-axis and then a rotation about the y-axis. Okay, so you have to multiply the matrices just in the opposite order. This is Ry of epsilon that we had. This is Rx of epsilon. Again, this is a matrix multiplication and this gives us the square matrix given here. This would be the square matrix corresponding to a rotation about x-axis followed by a rotation about y-axis by the angle epsilon. Both rotations are by an infinitesimal angle epsilon. All right. Again, I remind you, when you make this multiplication, remember to retain only terms up to the order epsilon square. Okay, always neglect terms of order higher than epsilon square. Okay, now we are ready to figure out the exact way in which the rotations about different axes fail to commute. You just have to find the difference. Rx of epsilon, Ry of epsilon minus Ry of epsilon, Rx of epsilon. Okay, again, this is the rotation about y-axis followed by a rotation about x-axis. Here is a rotation about x-axis followed by a rotation about y-axis. If the final result are the same, right? If the result of these two rotations in different orders is the same, then this difference would be 0. Okay, but we can check. We have these matrices. Rx of epsilon, Ry of epsilon is given here. Ry of epsilon, Rx of epsilon is given here. Just subtract and you see that the first term is 0. 1 minus epsilon square divided by 2 minus 1 minus epsilon square divided by 2, that's 0. The second term, 0 minus epsilon square, is minus epsilon square. In the same way, you can find the other components, other elements of this matrix, and you get this square matrix. Okay, clearly we see that this is not 0, which means that, again, quantitatively we are seeing that rotations about different axes do not actually commute. It matters which rotation is carried out first. Okay, now we see an interesting thing here. The first thing we notice is that if we had chosen earlier to neglect terms of order epsilon square, right? Sorry, terms of order epsilon square and higher order, right? Then this matrix would be 0. This would be the 0 matrix. All right. If you had chosen to keep only terms up to first order in epsilon, then the epsilon square term would be neglected and this matrix would be the 0 matrix, which means that infinitesimal rotations do commute, right? Infinitesimal rotations about different axes do commute. Infinitesimal rotations commute. We have already seen this again in classical mechanics when we discussed rigid body motion. We came to this conclusion that infinitesimal rotations commute, and using this fact we tried to associate a vector with infinitesimal rotations, if you remember it. Okay, and for the exact reason that finite rotations about different axes do not commute, we were not able to assign a vector, or we were not able to associate a vector with finite rotations, but we could do this for infinitesimal rotations because infinitesimal rotations commute. All right, so that's the first result that we see from here. Okay, the second and the important result that we have is the manner in which rotations about different axes fail to commute. Okay, this gives us the manner in which rotations about different axes fail to commute when terms of order epsilon square are kept. Okay, so let's look at this again. Rx of epsilon, Ry of epsilon minus Ry of epsilon, Rx of epsilon is this matrix. But this matrix can be written as, if you look at this, all right, we could insert a 1 in here along the diagonal, 1, 1, 1, and then subtract the identity matrix. So we could write this as 1 minus epsilon square 0, epsilon square 1, 0, 0, 0, 1. Right? We have introduced a 1 along the diagonal elements. We just have to subtract out the identity matrix. Okay, so this is the same as this matrix minus 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, but this matrix itself, is actually Rz of epsilon square. Right? That is, we already have Rz of epsilon here. You put epsilon square instead of epsilon, and again neglect terms of order higher than epsilon square. Okay, so R from here, Rz of epsilon square would be the square matrix with elements. This is 1 minus epsilon square by 2. If you put epsilon square instead of epsilon in here, this term would become epsilon raised to 4 divided by 2, which is a higher order term. Neglecting that, the first term becomes 1. This is Rz of epsilon square. Okay. The second term is minus epsilon here. Instead of epsilon, if you substitute epsilon square, this becomes minus epsilon square. Okay. And here the term is 0 again. This term, again, if you put epsilon square instead of epsilon, this becomes epsilon square. This is again 1, because if you substitute epsilon square instead of epsilon here, this would become epsilon raised to 4. Okay. So this is epsilon square 1, 0, 0, 0, 1. Alright, so that's this matrix. That is this matrix. So we can write this matrix as Rz of epsilon square. What's Rz of epsilon square again? It is Rz of epsilon with epsilon replaced by epsilon square and higher order terms neglected. Higher order terms neglected. Okay. So we have this result. Rx of epsilon, Ry of epsilon minus Ry of epsilon, Rx of epsilon is equal to Rz of epsilon square minus the identity matrix. But identity matrix is, you can write this as the rotation about any axis by an angle 0, right? Which means there's no rotation at all. So the identity matrix also can be represented as R any of 0. It means that you are making a rotation about any axis, but by an angle 0, which means that you are not making any rotation at all. So the identity matrix itself can be written as R any of 0, and we have the exact way in which the rotation matrices fail to commute, or rotations about different axes fail to commute up to order epsilon square. Okay. So this is an example of the commutation relations between rotation operations about different axes. Why do we do this at the beginning of a chapter about angular momentum? Because in quantum mechanics, we are going to define angular momentum as the generator of rotations. Okay, so once you define angular momentum as the generator of rotations, we are going to demand that under such rotations also, right, the rotations about different axes fail to commute exactly in this manner. Demanding this is going to give us the commutation relations among components of angular momentum. Alright, so we are trying to find these commutation relations among components of angular momentum. Alright, now this can be done, as I said, by defining angular momentum as the generator of rotations. Now, if you remember, we have done exactly the same thing in the first chapter. There we defined linear momentum as the generator of space translations, and using the properties of space translation, using the fact that space translations about different axes, space translations about different directions, space translations in different directions actually commute, we figured out the commutation relations between components of the linear momentum operator. We found that they actually commute, right? The components of linear momentum operator were found to commute because the translations in different directions, okay, commute, right? You could, in order to reach here, you could first move along the x-axis and then along the y-axis, or first move along the y-axis and then along the x-axis. The final result is the same. All right. So using the fact that the translations along different directions commute, we figured out that the components of components of linear momentum also commute. All right. Here we have the result that rotations about different axes fail to commute in exactly this manner. All right. Now this is going to give us the result that the components of angular momentum operators, all right, for example, the commutator of Jx and Jy, all right, we are going to find that this is not equal to 0. All right, and this exact commutation relations will define all the properties of these operators, especially they will give us the eigenvalue spectrum, etc. All right, so first we shall define the angular momentum operator as generator of rotations. Then using this result we shall find the commutation relations among components of angular momentum operator, and using those commutation relations we are going to obtain the eigenvalue spectrum. Okay, we are going to obtain the eigenvalue spectrum. And these are some of the things we are going to discuss in this chapter. Right? So I shall conclude for now. Thank you.